Oh hey, you caught me doing my favorite pastime, encrypting my data. Okay, admittedly that sounds like we're about to transition to a sponsor, but no, that's all me. What can I say? I just really like this subject. Encryption has to be one of the most underlooked inventions of the modern age. In an online world, we use encryption all the time. Heck, you're doing it right now. Whether we're simply browsing the internet, using a messaging app, or your trusty VPN. Nope, still not sponsored. Encryption is everywhere, and yet you never notice it. Despite its importance, it remains one of the most elegant and non-intrusive solutions tech has perhaps ever seen. Frankly, those cookie consent pop-ups could have used a few more iterations. So today, let's talk about it. How we got here, why we trust it, and all the neat little tricks that make it all work. In addition to theory, I also want to do some real coding demos to demonstrate how these concepts work in practice. I mean, this is a programming channel after all, so I better do some actual programming. Who do you think I am? A software executive? And with that, Bonnie Stu presents the exciting ecosystem of encryption. Act 1. The Power of Math. I think it's best to break the topic of encryption into 3 fundamental parts, so I'll be using the first metaphor I can think of for 3 pieces: the Triforce. First up, our Triforce of Power, the algorithm. This'll work. Ooh, first edition. See, back in the day we had this thing called DES, Data Encryption Standard, until I realized it wasn't very good. Now don't worry, you don't have to read all that, let me spice it up a bit. Developed at IBM way back in the 1970s, DES is a symmetric key algorithm that utilizes both substitution and permutation methods. And by the end of the decade, DES was approved as a standard encryption algorithm, but not without scrutiny. The biggest point of contention was the relatively small key size of only 52 bits. This change was suggested by, at least partially, the NSA. Bro, I kid you not, there's this whole subplot here where NSA proposed suspicious changes to the algorithm. Essentially, the fear was they were creating a backdoor only they knew about. This claim stems from the recommendation to shrink the key size, as their improvements to the substitution step didn't require a larger size. In fact, the NSA originally wanted a key size of only 48 bits, until 52 was decided upon as a compromise. But 52 isn't even divisible by 8. What am I supposed to do with half a byte? Obviously, this conspiracy is never being confirmed, and investigation concluded no tampering. But honestly, this claim may not be entirely unfounded. Let's just say there's a pretty blurry line between cyber analyst. How do I put this on? And cyber criminal. However, it's all a bit moot anyway. By 1998, a specialized machine known as Deep Crack was able to break a DES key in under 52 hours, or about 2.5 days. In modern times, even an outdated GeForce GTX 1080 Ti, remember those things? Can break a key on average in about 2 weeks, or a month to exhaust them all. You know, maybe instead of mining Bitcoin back in the day, we should have been breaking DES keys. Like I said, blurry line. By 2002, a new encryption standard had been chosen, AES, which stands for Advanced Encryption Standard, and safe to say, this one was better. Although I could swear it stood for Alternate Encryption Standard, but whatever. Technically speaking, it originally had a Dutch name. Yeah, I'm gonna stick with AES. And although I'm not experienced enough to explain how much more advanced AES is, I think we can at least agree on one thing. The Dutch always do it right. And that's not to say data encryption standard was lost to the sands of time, as several successors emerged over the years. For example, triple DES, which uses 3 keys, or even 2 keys sometimes, which is confusing. And ICE. No, not that ICE. Definitely not that ICE. No, this ICE stands for Information Concealment Engine. Wow, someone had a thesaurus in their pocket that day. You know, I find cryptography names fall somewhere between very literal and very forced. Or just, plain boring. And I haven't even mentioned Alice and Bob yet. And that is how AES became, and still is, the standard algorithm for symmetric key encryption. It's here somewhere. I'll take the Dutch version. And now, let's see it in code. Let's start by creating a crypt type to wrap our cipher object. Oh, this is a Go, by the way. This object is of type cipher.aead, and I'll be honest, I have no idea what that means. See, this is an interface that can represent a variety of cipher algorithms. To select AES as our cipher, from the AES package we can use new cipher. This function wants the aforementioned key, which I haven't really explained yet. We'll talk details later, but for now we can just use an empty byte slice. To use 256-bit encryption, we need a key length of 32 bytes. Makes sense, right? 32 bytes, 8 bits per byte, 32 times 8 is 256. Now, new cipher doesn't return the cipher outright, but something called a block. We can then chain this block into another method which does return the cipher. Don't worry about the technical details of this part, we're wrapping it in a function so we don't have to think about it again. Finally, we create the crypt object and assign the cipher. To perform encryption, we'll need a plaintext, and we'll return a ciphertext. From this cipher object we call seal, which has a lot of parameters. We can actually ignore most of them, but we do need something called a nonce. Again, we'll touch on this later, so we'll just create our patented empty byte slice. As for the size, to ensure compatibility with our cipher, we can use the non-size function. Note seal doesn't actually return an error, so we can just return the ciphertext outright. As for decrypt, the flow is very similar. From the cipher object, this time we call open. Its parameters are near identical, so we can fill them in much the same way. Note this time open does actually return an error, and it's really important we handle this one. Encrypting may always succeed, but decrypting can certainly fail if we use the wrong inputs. Finally, from our main method, we create a new crypt object. Let's call encrypt with some plaintext, and print that to the console. Then let's pipe that straight back into decrypt, handle any errors, and print that to the console. Giving it a run and we see exactly what we want, an encrypted string followed by successful decryption. And it really is that simple. I want to give some serious recognition to all the amazing people who contributed to these algorithms over the decades, either developing the algorithms themselves or implementing them in the standard libraries. These guys are among the real heroes of the digital age, and without their work, who knows where tech would be today. Except the NSA, we don't trust them. Also, quick editor note here, this is the most American logo I have ever seen. You know what I mean. Now that's not to say we've done everything correctly. Let me take this off. Time we address some of the parts that we skipped over, because frankly, this isn't exactly good practice. Act 2. The Key to Wisdom. With the Triforce of Power in our position, eat your heart out, Ganon. We turn our attention to the next piece. If the algorithm gives encryption its power, then the key grants it its wisdom. You can think of an encryption key like a second input. The same key plaintext pair will always produce the same ciphertext. And that ciphertext paired with that same key will always produce the same plaintext. Keys themselves can take many different forms depending on the cipher. For a Caesar cipher, this is just a single letter. For a substitution cipher, it's 26 letters. For AES, this is 128, 192, or 256 random bits. A key space defines the number of possible keys. For a Caesar cipher, this is 26. For a substitution cipher, this is 26 factorial. For a bit-based key like AES, this is 2 to the n, where n is the number of bits. Question. How much bigger is the key space for a 256-bit key versus a 128-bit key? Wait, what? I didn't realize this was going to involve homework. Huh, what do you know? Anyways, this is actually a good question, because the magnitude of key spaces are not always intuitive. Let's consider a simpler example of only a 3-bit key. 2 to the 3 is 8, and we can easily list all possible keys. Now what if we wanted to expand this into a 4-bit key space? Well, we can take what we already have and just add a 0 in front. Then we can take everything again and change that 0 to a 1. As you can see, by adding just a single bit, we have doubled our entire key space. And that's the answer. Bit-based key spaces don't grow linearly, they grow exponentially. So the key space for a 256-bit key is not twice as big as 128, it's 2 to the 128 times as large. Of course, this also works in reverse, as taking away just a single bit halves the entire key space. Honestly, that's why a key length with only 52 bits, thanks NSA, is kind of absurd. Granted, and I'm bringing out the Casio for this one, 2 to the 52 is still a pretty big number. But let's assume we can test 1 billion keys every single second. This will take about, what is this, 4.5 million seconds or so? And the fact that we don't need exponential notation anymore is kind of troubling. This is about 52 days. Not a short amount of time, but nowhere near enough. And this is to exhaust the entire key space. On average, you'll need to check about half of them. Now let's do the same for a 256-bit key. First of all, bruh, that's a 1 followed by 77 zeros. Second, dividing by even a trillion doesn't even make a dent. Honestly, trying to quantify this number is kinda pointless, which in turn is the point. These astronomical magnitudes are exactly what you want from your key space. Unless you have an eternity to wait, you're not brute forcing this one. Oh, finally. It's time to do some crime. Now, it may have taken longer than the lifespan of the universe, but I can finally read what Alice said to Bob. She said, and I quote, "Sup?" Huh. You know, I wouldn't have expected that from her. Honestly, I'm just surprised the sun hasn't run out of fuel yet. That should have happened a long time ago. Oh, no, there it goes. Hello? In code, we can use the read function from the RAM package to fill our empty key slice. Now make sure you're using the one from the crypto library, not the near identical one from the math library. The concept is the same, but the crypto variant ensures the resulting sequence isn't easily reproduced. Running the app creates a new ciphertext every time, since every execution uses a new secure key. And this works great, but it does beg the question, how do we remember the key? One solution could be to save the key to disk. First, we modify our main file to generate a key. Then save it using a file pipe. Next, we read the key from input and pass it as a parameter to the crypt constructor. Finally, we can simply pipe the key into the command to execute our crypt loop. And if all this implementation is a little bit prototypey, the solution as a whole isn't a bad idea. For example, you could just store your key on a flash drive and secure your files that way. You might call this a hardware key. But what if you forget to bring it or just, lose it outright? Wouldn't it be better if we could just remember the key instead? And although memorizing 256 bits is a little outside my skill level, what if we could remember something easier instead? Perhaps some kind of word that we could pass to... What am I doing? You need a password. Password-based key derivation function 2. Damn. I'm gonna put that into the literal category, but bonus points for sounding badass. Like the name very clearly suggests, this function can generate an encryption key from a password string. And if that sounds kind of like password hashing, that's because it is. Honestly, I couldn't find too much history on this one. I mean, whoever wrote this book couldn't. But any security concerns it does receive mostly just reflect the same concerns of the underlying hashing algorithms. Collisions, brute force attacks, rainbow tables, no need to go into details here. Although you could say using a password to derive an encryption key does also simplify the cracking task. Instead of exhausting an astronomically large key space, cracking boils down to, can we guess the password? And yeah, those are valid criticisms, but sometimes you have to sacrifice a little bit of security for convenience. And no, before you ask, this algorithm does not support two-factor authentication. That's function free. In code, we start by defining a few constants. We'll still want a key size of 32 bytes, and we'll need to define the number of hashing iterations. The more iterations, the more secure, but the longer it takes to compute. But honestly, I don't see why we can't go ham on this. 100,000. Next, we define another constructor, this time taking a password as an input. Using the pb2 package, we call the key function. For the hash, we'll use SHA-256, and we'll also provide the password, iterations, and key length. We did miss a parameter, however, something called a salt. Now hear me out, we're gonna skip this part. Unlike the nonce, this length isn't so strict, so we'll just use a good size of 16. Finally, we can chain into the other constructor and password generated key. In main, instead of reading the key file, we'll read the password from the console then use that to build our crypt object. When we run the program, we enter a password and the encryption proceeds as expected. Now this flow is looking better, but it has exposed a bit of a concern. Every time we use the same password, the resulting ciphertext is also the same. And this makes sense since the same key is being generated in both cases, but it's not exactly ideal. Although the plaintext remains obscured, their equivalence does reveal they contain the same plaintext and use the same password. Now that may not actually equate to much, but in general we would prefer not to leak information like this. Now a solution could be as simple as using a unique password for every encryption. I mean, you're supposed to do it for every website anyway. But let's face it, you've been using the same password since you were 12. I for one haven't. Yeah, we're gonna need a better solution. Act 3. The courage to commit to a metaphor. If the key was the wisdom, and the algorithm is the power, then the salt gives encryption its courage. Yeah, it doesn't really make sense, does it? Damn, I thought I was cooking there. But maybe that was just the salt talking. In a hash-based algorithm, a salt is simply just a random sequence of bytes that is added to the password during hashing. This essentially changes the password, so the resulting hash is completely different. Like how a salt is added to a dish during cooking to change its flavor. At least I think that's where the name comes from. I'm gonna create an ambiguous category. And that's all there is. That's all it takes. No wonder no one wrote a book about this one. You don't even need to be sneaky with the salts. It can be stored in plaintext alongside the hash. Because without the password, the salt gives you no more information about anything. Honestly, I don't mean to get so passionate about salt. But I think this is such a beautifully simple solution to what initially seems like quite the tricky problem. In code, we'll once again use the RAM package to fill our slice. And that's it. Wow, maybe I really did overhype this. But if we give it a run, we see every time we encrypt, we get a new ciphertext, even with the same password. But the issue still persists when using the key file approach. I mean, it will once I recode that part. Yeah, I didn't plan that very well. Now remember this little thing called a nonce? Well, a nonce is a type of salt whose name is short for only once. Sort of? That's going in the force category. I don't know, I guess it's cute. The idea here is this specific salt, the nonce, should be unique for every single encryption operation. This process ensures unique ciphertext every time, regardless of the plaintext or even the key. In code, let's once again, use the read function to fill our nonce slice. For decrypt, it's not quite as simple as repeating the process, but let's see what happens. Running the app and it didn't work. Something about message authentication failed. This error occurs because we're using a different nonce for both the encrypt and decrypt. What we need is the same nonce. If we inspect seal, we'll see the first parameter is named destination. If present, the seal function will append the result to the destination slice. Currently, we're not using it, but if we pass nonce as to destination, then the final result will contain both the nonce and the ciphertext. In decrypt, we can remove the nonce creation code as we'll be extracting it from the ciphertext. Using goes slice operations, we'll first slice from the start of the array until nonce size. For the ciphertext, we'll start at the nonce size, then slice to the end of the array. Running again, and it all works as expected. Now every time we run the app, we get a fresh ciphertext even with the same key file. And that's it. I really mean it this time. That was the last security concern we need to address. The algorithm, the key, and now the salt. Our encryption triforce is finally complete. Okay, I think it's enough of that. Obviously, it's a bit of a shaky metaphor. Put it in the force category if you want. But I did say it was the first metaphor I thought of. One of the reasons why I find encryption such an endearing topic is because it's not just a piece of technology. It's a story. A whole history of brilliant minds, masterpieces of mathematics, all coming together to become something more. Honestly, this channel definitely lost its spark for a while, and there's a good reason for that. With the tech industry becoming so sloppy, we'll call it, I wasn't sure I even cared for programming anymore. I didn't appreciate what it was becoming. But if this video was any indication, yeah, I do still hold a lot of passion for this subject. Also, these motion graphics are dope, right? I actually coded them myself in the Godot engine. But that is definitely a topic for another day. Now, it may have taken some time, 3 to 4 months in fact, but with this project I was finally able to find that spark again. To remember why I got into programming in the first place. Coding can be an art form. The application is the canvas. And the project? Well, that's my story. Damn, now I'm cooking. And you know what? I think I'm gonna quit while I'm ahead. It didn't make it into the final script, but I did actually beef this thing into a more substantial application. If you want to see the source code for that, you'll find the repo linked in the description. Also, if you want to see the code from the demo specifically, including the final prototype, you'll find that on the video branch. And with that, I don't know what to tell you, I'm tired. If you enjoyed this video, and I mean like really enjoyed it, drop a like, leave a comment, subscribe? This channel's actually still really small. The next video shouldn't take 3 months, more like 2. So I guess I'll see you when I see you.